All right, last time we were talking about alkynes, okay? So we just kind of stopped right here. Are any questions about anything we talked about last week? Okay, any questions? All right, so let me just circle back a little bit about right here. When we were naming alkynes, remember we kind of had this situation here. Okay, so the naming for this alkyne is 2-propynyl cyclohexane. Cyclohexane is the parent chain, and at the directly connected to it, it's an alkyne, but the alkyne starts at the 2 position, so that's why we named it 2-propynyl cyclohexane. Okay, are there any questions about nomenclature? Okay, so use the examples in the homework. I think that's a good way to figure out what kind of nomenclature type problems you'll be asked. I don't like to make any tricky ones, just straight to the point, so you can kind of increase your knowledge here of naming different compounds. Okay. Don't worry about any of the reactions yet. We just started talking about them last Thursday, so don't worry too much about the mechanisms, but start thinking about how these reactions work, because as soon as we go through some of these reactions, we'll have to apply them in the homework towards synthesis. Okay? All right. So last time we left off on electrophilic addition reactions of alkynes. So they are very similar to alkene reactions. Okay? So just think of, when we had an alkene, we added HX or HBr, HCl across the double bond. So if it's symmetrical, well, alkynes will almost always be symmetrical unless it's a terminal alkyne. We'll see some situations where that reactivity will change. Okay, so in this case, we have HBr adding across a triple bond, and we get 2 isomers, the Z-alkene, 60% yield, and the E-alkene, 40% yield. Okay, so if it was asked of you, you would want to draw both of them, okay? Because it's very tricky to predict which one would be favored based on the conditions. Okay, so to save ourselves some headache there, you will want to draw both alkyne isomers, okay? And we'll see a situation where it's not symmetrical, okay? Or, there's excess HBr. So we'll talk about that soon. Okay, so how does this work exactly? So the mechanism is not well known. Different books pose different mechanisms, but you kind of think of it as doubly electron rich. So if an alkyne has 2 additional pi bonds, you can think of it twice as reactive as a typical alkene, okay? So a typical mechanism people show in the book and on the web is that one of these bonds remember, alkene is electron rich, so electron rich pi bond, okay? So we could kind of think of that as our nucleophile. So that's going to be our nucleophile right here, okay? So what's the nucleophile going to be attracted to is the hydrogen from the HBr, and that will break that bond, and you'll get the hydrogen onto the alkyne. So it's symmetrical, so it doesn't matter which H you add, where the H goes. You just pick a side. So here, let's just make the left side where the H gets attached, okay? And then here, the positive charge. So notice here that a positive double bonded carbon is not very stable. So this reactive intermediate really requires a strong acid. So not very stable. So I'll just make a note here. Vinyl or a C double bond C group. Carbocations are not stable. Okay, so they rarely form. Remember, we talked about regular carbocations. They're stabilized by adjacent carbon groups. Well, this carbocation is actually not in a p orbital. Okay, it's actually perpendicular to all these other groups here. So this this carbocation here, it's actually in a p. Is the p orbital it's involved in is flat. So it's not the best, it's not very stabilized because of the orbital it's in, okay? So when we break this triple bond here, we're actually breaking one of the pi bonds, and now that carbocation is in a p orbital, but it's not in one that can be stabilized by these adjacent carbon groups here, okay? So see these adjacent carbon groups here? These groups can't stabilize the positive charge by hyperconjugation. Okay? They can't stabilize that because these orbitals here, see, they're in different planes. So the CC bonds and positive charge are in different planes, okay? When they're in different planes, they can't overlap. Remember the p orbitals, they have to be side by side. Well, if one's perpendicular, there's no way for them to interact like that. Okay, so these orbitals, they can't help the carbocation. That's why we never really drew alkenes with carbocations, because they're not very stable. And that's one of the reasons they don't really participate. Like if you have an alkene and a leaving group, they don't participate in SN2 reactions. Okay? Or SN1 reactions for that matter. All right, so let's talk a little bit about now what happens next. Okay? So now, let's just redraw this. So I'm going to just redraw this group here. Okay? Just so I could, don't have to erase that. All right, so what do you think is going to attack this positive charge? Well, we have a Br minus floating around. What do you think that's going to do? Any ideas? Yeah, just going to be attracted and do nucleophilic attack. Now it can bond to this carbon because this is a very, very reactive intermediate. So that will bond to that carbon, and then we get the product here as the alkene, and we get the, all right, which isomer is this? Let's compare it to that group above. It's the Z alkene. So this is their Z alkene. So the Z isomer. So we get the Z alkene here. Okay. Boom, boom, boom. All right. Bam, bam. Okay. All right, so that's one way to form this E alkene, okay? Now, you may be wondering, how does the E alkene even form? Like, is there a way that forms? So we'll talk about how the E alkene now forms, okay? But are any questions on this mechanism? So, like the alkene, you generate the carbocation on the more substituted side, but in terms of alkynes, they'll be equally substituted because you can't have more than one group, more than one bond to a triple bonded carbon, right? So you can only see, unless it's unsymmetrical, there'll only be like one pair of products, cis or trans alkenes, okay? So you form the carbocation, then it's trapped immediately by the nucleophilic X, and then you get the haloalkene here. In this case, the bromoalkene. Now let's talk about E to Z isomerization. So let's go to E to Z isomerization. All right. So let's take, or it could be vice versa. But let's take the Z isomer and let's convert it to the E isomer. All right. So BR there. Okay. All right. Okay. So if I were to, remember an alkene can also be attacked by acid, right? So if I were to attack this acid, where do you think the H would want to go? On the carbon with the hydrogen or on the carbon with the bromine? Yes, carbon and hydrogen. Good. Let's see why that is. Okay, so we're going to add this hydrogen to the carbon with more hydrogens on it. Okay, so we get this structure. All right, we could draw this carbon out too. Now this carbon doesn't have a full octet anymore. Okay, now we have this carbocation. All right, but this carbocation can also so this carbocation, it has a resonance structure. How can I draw a resonance structure with this carbocation? Let me just draw in something for the bromine. Maybe that will help us see that. So is there a resonance structure we can draw using maybe something with the bromine? So we can actually use these bromine's electrons and push them down to form a resonance structure. Now the bromine's carbon atom, the carbon atom attached to the bromine, now it has a full octet, even though the bromine now has a positive charge. So even though the bromine has a positive charge, this is an important resonance form that contributes to the stability of this structure, and why it's preferred to be protonated on the left side of the carbon, of the left carbon atom of the alkene. Okay, so now this is a resonance structure here, so we could draw resonance structures with there. Okay, so that's why this form is preferred, and it protonates predominantly on the left hand side. Okay, so that's why it protonates there. Okay, so now we got to look at this structure. So let's redraw this structure. Okay, so we're going to redraw this structure again, just so I can keep the resonance form here. All right. Okay. Now we need to somehow get to the cis alkene. So remember, when we ever generate carbocation, what can happen around the CC bond? What can happen around the CC bond if we have free rotation? Say it again? No, don't think about delocalization. Remember what happens, like alkanes at room temperature, they can rapidly convert between many conformers. All right, so what can we do about the central CC bond here? What can we do to move the groups around the carbon atoms? What can a molecule do freely at room temperature? If we think about chair conformations, we interconverted. So we can go between conformers, right? So we can actually rotate these bonds here. So we're going to rotate. So rotate around the CC bond, and now we get the carbon atoms like this. So now the carbon atoms are on the same side of that internal CC bond. And now we get this Br here still. And the carbocation's right there. And we still get the two H atoms right here. Okay? So, and then now, if I think about what's in solution, remember this hydrogen can also come off. So this Br can come around and just take this hydrogen again and reform the double bond. And now we have the Z alkene. Okay. Okay. Yeah. Oh, I meant the right BR there. Okay. So now we have so if we compare this alkene to the ones we drew above it, this one, so look where the H and Br are. The H and Br are right here. So that's now the E alkene. So you can see why if we have acidic conditions and we let that react, eventually the Z alkene or the E alkene, they can rapidly interconvert. And that's why we get a product mixture here based on these ratios. So it's hard to predict what the ratio you'll exactly get unless you do the experiment yourself. So this is the Z alkene. Sorry, the E alkene, my bad. All right. So what happens here, you have minus H plus in this direction. And then if you're going the reverse direction, it's plus H plus to go backwards. So usually that's how we represent something that can go back and forth in equilibrium. Okay? All right, are there any questions about that interconversion? This is merely to explain why we see two products. Okay? If anything, I usually don't even ask about this. I just ask, how do you get to the mechanism and the expected products. So, no, you could get E and Z alkenes when you react an alkyne with HBr. Okay. Are there any questions about that? Yes, Captain.
Why was it that the left carbon was able to rotate but not the right one?
It doesn't actually matter. You can rotate either one. Yeah, I just chose one. Right. Good question. Yep. Okay. Any other questions? No? Okay. So that's how we get that that scenario there. Okay? Okay. All right. So you notice here we stopped at the alkene, but what if we use excess HBr? Well, then you can actually react it even further. All right. So let's go to excess HBr now. All right. So if I say two equivalents, that means I add 2 molecules of HBr, so the alkyne can actually react twice, okay? So let's talk about how this works. Okay, so you react it twice, you actually get two equivalents of both the hydrogen and the Br adding. Okay, so the two hydrogens will add to the same carbon, and then the two bromines will add to the same side. Okay, so really this technique is only suitable for a symmetrical alkyne. Because what do you think happens if the alkyne is not symmetrical? How many different products will you get? Yeah, two, I heard it. So you get two different initial final products, right? Well, that's not good if you just want one product, so you'll have to separate it. And plus, if you don't, if you get a mixture, you're using half your yield, or statistically half your yield, to the production of another product, and that's not good in terms of like chemistry. If you want to isolate, if you're using a targeted synthesis, it's not very good. Okay. All right. So how does this work? Let's talk about the mechanism. Let's write this a little up below here. Okay. Okay. So we know the alkyne initially goes through one equivalent of HBr. Okay. And you get maybe the E alkene, or this was the Z alkene. Okay, so this is the Z alkene. All right. So the Z alkene here, because these two groups are on the same side. So here's the Z alkene. So Z. All right, the higher priority substituent on both of the alkene carbons are on the same side. All right, but how do we get to the, how does the other product work? Or how do we get to the other product? Okay, so we kind of saw it initially here. HBr. Now we said that the hydrogen goes onto this carbon because we can generate a carbocation that is resonance stabilized. So it stabilizes by resonance. Okay? And we saw this resin structure from the bromine, like so. Okay. So, when mechanisms, if it's important to show the resin structure, show it. But you might be wondering, okay, what structure do I use to go forward? It doesn't matter. Use either structure you want, okay? This one, I'm going to use the right-hand structure. So, bromine, so we know Br is floating around here. I'm going to use it to attack this carbon and break this double bond and push it back up to bromine, okay? So if I do that, I will now get my final structure, which is two Brs on the same carbon. And so that's how we get to the final structure right there. And I'll just put the hydrogens just to show where the hydrogens add. So it looks like we add HBr in the same direction across the triple bond twice. So the takeaway here is that the BRs you're going to form a dihalo alkane. And when they're both on the same carbon atom, this is what we call a geminal dihaloalkane. So this word geminal means both groups / halogens on same carbon atom. That's what geminal stands for. Vicinal is when they're right next door to each other, like next door neighbors, adjacent carbon atoms. Here, geminal means the same carbon atom. So that's what geminal dihaloalkane looks like. Both haloalkanes on the same carbon. Okay, are there any questions about the mechanism? So you see the mechanism is pretty similar to alkenes. So you could kind of think a triple bond is like an extension of alkene reactions. Okay. All right. Are there any questions on that example? Do we need an explanation why, repeat the explanation, why the halogens go on the same carbon? Or is that clear by this resin structure here? Is it clear by this resin structure here? Okay. Alondra.
So does the excess, like this reaction, only happens within Z?
Oh no, it could actually happen with either of them. So it doesn't matter. You'll get the same product if it's Z or E.
Oh.
Yeah, cis or trans E or Z, it doesn't matter. Yeah. So I'll say here, this reaction works for E alkene as well. So you can have both of these products occur. So for the E alkene, let's just draw it. You can also use this too. But just know, I showed the mechanism just for the Z alkene. But the same steps apply if you use the E alkene too. So don't be alarmed if you see the E alkene. The same steps apply as well. Okay, any other questions?
Did you have to show both of the resin structures, or we can just show it on one?
What do you mean?
Like the whole mechanism, like you showed the second resonance structure, can you also choose the first resonance structure to show?
Use the first resin structure to show the mechanism? Yeah. Just draw both to illustrate that it's resin stabilized, but then I could have used bromine here and attacked this instead. The reason I didn't choose that one is because I already had an arrow drawn on that structure, so it would look confusing. So that's why I chose a different one. But you can use either one. Okay? All right. Now, what happens if we just use a terminal alkyne? Turns out things are a little bit different if we use terminal alkynes. So let's use that example next. So addition of HX. So in this case, X is Cl, Br, or iodine. Okay? Two terminal alkynes. All right. So terminal alkyne, instead of a carbon here, you have an H. So let's write the H here, just for illustrative purposes. All right. Let's use HI. So HI is particularly, I think you need to lower this temperature just so you don't get side reactions. Okay, so HI here, let's do one equivalent. All right. So what happens here, this reaction is very difficult to control. You can't actually control this, so you get a mixture of both the alkene, so you don't have to worry about cis or trans here because the alkene one product can only form when it's terminal alkyne because there's a preference on which side it wants to add. But you can't stop there. It actually goes forward one more time to give you the completely reacted alkyne. So you go to the alkane. Okay. It's possible also to push this to completion if you use more than one equivalent. But sometimes maybe that's not reasonable. Because HI is not very, I don't think it's very cheap. All right. So here I will mention, usually difficult to limit. So RXN stands for reaction, okay? It's very difficult to limit the reaction to addition. Of one HI molecule. So you have 1 mole of alkyne, and you only add 1 mole of HI. You can't just stop at 1 HI molecule. Once the alkene forms, another molecule of HI will just add to that because now it's technically more reactive because of the iodine molecule in there. So it's very hard to stop. So these reactions aren't as clean as we had hoped. So there's always room for improvement. Okay. Are there any questions on that example? All right, so the takeaway here, HI adds across a triple bond. Usually you can stop, HX, you can stop at the, you usually have mixtures of both the alkene product, and if you really want to push it to the alkane, you'll add more than 1 equivalent, okay? But the takeaway here is that you can actually stop at the alkene forms here, depending on what you use, okay? But in reality here, if you write both products, okay, you'll get full credit, all right? So what I would do is every time you see an alkyne, 1 equivalent, just write the alkene products. And if you see 2 equivalents, go all the way to the alkane here, the dihalo alkane, okay? Don't worry about what ifs or, what if it's a mixture. That's really something you can't really predict reliably. All right. Okay, are any questions about the reaction we went over so far? Electrophilic addition of HX, hydrogenation of alkynes to alkenes. And then I think that's it. The other thing we did is preparing alkynes, so using them in SN2 type reactions. Okay, so here for the more synthesis type reactions, just be able to recall some of the concepts we learned back in 18A because they build upon each other. Okay, so that's part of your your chemical toolkit here, or your tool belt. All the ways you can now, build up molecules from scratch. Okay, so that was 2, electrophilic addition. So first we talked about hydrogenation, and then we talked about electrophilic addition. So there's a little trend here to kind of follow the reactions we saw with alkenes. All right, let's go with reaction type 3, Anti-Markovnikov. Addition. All right, so this only works with HBr. We saw that with HBr last time with alkenes, so 2 terminal alkynes. Okay. So guys, mechanistically, don't worry about this one. Very similar to the ones we saw for alkenes, okay? So, this only works for terminal alkynes. So we don't actually see this with internal alkynes. And we'll go over some reactions in a bit about the internal ones. All right. So remember we have HBr, peroxides, R2O2, H-nu to activate the alkyne or the radical reaction, one equivalent. Okay. So what do you get? You get the H actually adding to the opposite side, the carbon with no H. So that's where the H adds. And then this H is where the original H in alkyne is. Okay? And then you get a Br here. And then what also happens is this alkene can then further react. So you actually get a mixture and you end up getting both bromines again on the same carbon because of the effects of Anti-Markovnikov. Okay? All right, so you can actually get both of these products, and the mechanism is very similar to the alkene one. Mechanism is similar to alkene reaction. So if you need to recall that, please look at the notes when I did the alkene version. Very similar. Don't need to worry about that one. Okay, but the alkyne, the major one here is you go to the alkyne. The bromine is on the least substituted carbon atom. So it's kind of the opposite we saw in our previous examples there. Okay. All right. Any questions so far? So let's see here, Anti-Markovnikov. Let's go over what Anti-Markovnikov means again. H adds to more substituted carbon, more substituted carbon atom of CC bond, bond. Okay. And then the bromine is the one that adds to the least substituted. So Br adds to least carbon atom. All right, so is a reversal of selectivity. And oftentimes, when you form an alkene, that's also reactive, so that will also react. So it's often hard to stop at the initial stage, okay? Okay. All right, so we got Anti-Markovnikov. We saw that with alkenes. See that again with alkynes. All right, number 4. How about halogenations? Of alkynes. So let's draw our internal alkyne, our symmetrical alkyne example. All right. So here's bromine, Br2, and here's my solvent, CH3, CO2H. Right, so this is just our solvent. It's not really going to do anything. Okay. So in this case, what do you think is going to happen here? Remember when Br2 reacted? When Br2 reacted with an alkene, it formed a dihalo compound. Now we're actually going to form a similar thing here, except we're going to stop at the alkene stage, ideally, and then Br here, Br over here. Okay, so we stop at the Br2 stage here, the dibromo compound. All right, so this will form pretty much exclusively here. So once all the bromine is used, usually you stop at this stage. Okay. Now, what if we have two equivalents? What do you think is going to happen to that alkene double bond? Yeah, so we're going to break that double bond apart and then add another two what? Yeah, another two bromines. Good. So what you get here is, let's just draw, oops, my bad. Let's draw the backbone. Oops. All right. So this red bond is where the double bond used to be. So now we're going to add two bromines again. So now we get a tetrabromo compound. All right, so that's the compound we get there as we add two equivalents there. So sometimes this is wanted. Sometimes you want this. Depending on what you're doing. So sometimes maybe you need this compound. And sometimes you can actually use this compound for further functionalization, especially if you're making, a very large compound, and maybe you need some halogens on there to do useful chemistry right there. Okay? But yeah, that's how you can functionalize it even more, and then you can turn this compound into other things using some of the reactions we went over. Okay? But that's how we can transform it. All right. Now how about a terminal alkyne? So let's go over this example. And we'll take a little break here. All right. Br2. And then CH3. CO2H. All right. So the only difference here is that the alkyne is terminal. So you're going to get, again, an alkene. So let's draw the alkene right here. But at one end, there's going to be a hydrogen instead of a other carbon atom. Bromine and bromine. So here we see how we can get functionalized alkenes based off transformation of the alkyne there. Okay. 6, okay. All right. Let's take a little break here, 10-minute break, and then we'll talk about reacting alkynes with water. That's like we saw with alkenes. Okay? Yes.
Please be patient with me.
Okay. It's new year,
I
of
forgot
course.
to sign up for this campus wire octave. buttons because I've been busy with my speech.
Yeah, just register, and then when I check it,
Okay.
by the time I check it, I'm gonna check it like
Yeah, 'cause
maybe
I know
later
you
this
haven't
week.
graded it yet,
Yeah, so just sign up and you'll be
Okay.
fine.
Okay. Thanks.
Yeah.
I have a question.
Yeah, what's up?
So, I had messaged you over the weekend.
Oh yeah, sorry. So no, you don't have to write that.
Oh, we don't
Yeah,
have that for?
It- only experimental type things. You're
Okay.
fine. Yeah. Okie dokie. Hey Kim, what's up?
What did you say? Oh, right here. Look at which mechanism? Or like-
Oh yeah, so I said to look at the similar to how the alkene work, the radical reaction, but you don't have to really worry about that mechanism. Yeah, but it's basically the ones for alkenes. So that reaction also occurs with alkenes.
Oh,
So the mechanism last semester. So the
Oh.
mechanism is very similar. Okay, but if you just remember the thing about Anti-Markovnikov, you don't have to really worry about the mechanism.
oh, okay.
Yeah.
And then for the lab, you said we can just look at the directions of how to use the melting machine. We don't have to.
Yeah, so I'll go over the directions. So if that time you can just write the directions. Because look at there's instructions on the near the instrument. It might be a little different because it's a different model from the one that's in the lab manual.
Do I need to write those directions?
Well, you could just write, I mean, if you want, you could just, cut and paste maybe, or just write them if you want, but not necessary because we're going to go over it together as a
Okay,
class.
so I don't have to write those directions that are on the wall for the machine.
When you're like, when you go do it, maybe just like, just summarize what you did.
Oh,
So in case you have to use it again, you know exactly what to
Oh,
do. Because
okay.
we'll probably have to use that a couple of times this semester.
Okay.
Yeah.
So then, for the data table, do I
Yeah.
just write like what substance and the melting point? Like
Yeah, so you're gonna collect your results, and then you also have to make room to collect the results of the other groups
Okay,
because
so-
they're gonna record a certain sample,
Oh.
and you need to use all that data and plot it.
So can I have 3 columns, like my substances, like
Yeah,
my melting
whatever
points,
works
and
for
then
you.
plus
Yeah,
melting
sure. Like melting point, sample A, pure B, your mixture, and then you can put all the other mixtures.
Oh,
It'll be
okay.
like 20, 40, 60, or something like that, 80%.
Okay,
Yeah.
so I can just have the 3 columns.
Yeah,
like my
whatever
melting-
works for you.
Okay.
Hey, what's up?
Just have a question for that one that's actually on the oh, this one right here.
Yeah, what's up?
I know it's a different solvent. But
Yeah. So
what
they
I'm
just use
getting-
different solvent.
But what I'm getting confused on is like the structure of it.
Yeah.
Is it always going to be that same structure, but it's switching out? Because I know it's 2 equivalent, so we're going to have 2 BR2s or 4 bromones. But it's kind of be like the same flow, just watching out what the solvent is.
Yeah, just remember, anything on the bottom is usually just a solvent.
Okay.
So it just accompanies the reaction. It just gets everything in solution, but it doesn't participate in the actual
reaction.
chemistry. Yeah, it's just to get everything together so they can react.
Okay.
Yeah. Yeah. You got it.
Yeah, I've been practicing.
Good.
The little questions on there are pretty helpful
Which ones?
on that website.
Yeah, it helps you kind of review them, right?
Yeah, and then it's helping with the homework too.
Oh, good.
Yeah.
Great. Use that.
Pretty-
Alkene reactions.
cool if you getting lit. No, because I hung out with some Target people once. And we went to like.
All right. Let's talk a little more about these reactions, and then we'll end there for today. Okay? So right now for alkynes, we talked about pretty much all the similar reactions alkenes undergo, except maybe, like acid-base, deprotonation type reactions. But we went over hydrogenation, HX reactions, radical reactions with HBr, and now we did X2 halogenations. So now let's talk about how does water play a role. Can we hydrolyze alkynes? And it turns out we can. And we can actually form interesting, more functionalized compounds, more useful compounds, rather than halogens or, haloalkanes. We can go a step further. So, addition of H2O. So there's two types. Addition of H2O to an internal alkyne, or to internal alkynes. Okay. All right, so for alkynes, it's not as straightforward as alkenes. You can't just use sulfuric acid. And the reason is, remember, like I said, the intermediate here is a vinyl or a carbocation that's on a sp2 hybridized alkene carbon. Those are very unstable. So to help this process, to help sulfuric acid out, it's catalyzed, especially when you need to add water, a weaker nucleophile than, say, X minus. You have to use mercury salts, so Hg sulfate salts. All right, so this here is our catalyst. Okay, and what happens here is that you somehow get a carbonyl compound. Oh, that's my bad. You somehow go from this alkyne into this ketone, okay? And this is the only product that you observe. So we have to somehow get back to this compound. So this is the only possible product. So we have to somehow get to this compound here. How do we get to this compound? Okay. And you can also react with unsymmetrical alkynes, but this poses a problem because it complicates the reaction product mixture. Okay, so you can get the ketone on one end of the alkyne. So imagine we go to this side first. You go to that side, and that's product number 1 right here. Okay, but then you also get this product. So let's go back here. Plus. Now you have the methyl. 1, 2, 3. So this is when the water adds to this alkyne side. So you can get 2 possible products because it's unsymmetrical. So you get these yields almost pretty much statistically here, 50% for this molecule and 50% here. All right, so when it's unsymmetrical, you get a mixture of products. So actually, if you had a target, say the left molecule is your target, you don't need the right molecule, you'll be wasting half of your results here. So it's very wasteful if you get a mixture of products here. Okay? All right, so let's talk about how this works. So let's talk about the mechanism. Okay. So the mechanism, we're going to use the first alkyne we drew. So let's use the symmetrical version of this. Okay. So what the mercury does, it's just a catalyst. So usually we don't show it in the mechanism, okay? But here's what happens is, so you have water here, H+. So this combination, you're going to get you're going to first go through this process. You're going to form this reactive intermediate, an alkene and an alcohol group. That's called an enol. And we'll see this intermediate a lot in the upcoming chapters as well. So just be familiar that if you have an alkene and on that same alkene carbon is an OH group, that's called an enol. So an alkene plus an alcohol. All right. So this undergoes a certain rearrangement. So what this happens here is, this is a isomerization reaction where the molecule will rearrange some bonds to become more stable. That's called tautomerism. So tautomerism. So that's a special case of isomerization where a double bond and a hydrogen in the molecule switch places. Okay, so in this case, we have the same carbon atoms. The double bonded O forms, so you're switching the double bond from the carbon bond and putting it with now the carbon oxygen bond. And what happens here is that the H also switches places. It goes, so you can see here that one of these H's appeared right here. So this H right here moved where this double bond used to be right here. So it actually went right there, and that's called tautomerization. Okay? So you ever see tautomerization, just remember, okay, I'm going from my enol, I'm going to switch and form a ketone or double bond O instead. and the H will rearrange like that. So this happens pretty quickly. You can't stop it. It's unfavorable to stay in the brackets. So it pretty much does this on its own as a final step to the final product. Okay, but let's go over exactly how this works. Okay, so let's draw the individual steps one by one. Okay. So here's exactly how it works. So let's redraw the alkyne. Okay. So it's going to react with H plus. So the mercury, what the mercury does, it just makes this whole process faster. So I just left it out for clarity that the same steps apply. In your homework, you may see the alkyne first attack mercury, and then these steps will follow. Okay. So, but if we ignore the catalyst for now, this is basically how it works. Okay. So the alkyne, what do you think the alkyne is going to do to this free-flowing acidic hydrogen? It's going to pick it up like so right here. Okay. So when you do that, you will generate your carbocation. And it doesn't matter which carbon you bond it to. I'll just draw these carbons here, just to show where the hydrogen is going. So you get a plus charge on one carbon, and you get an H on one of the others. Okay. Now, where do you think, what's water going to do? Yes, so attack the carbon with a deficiency, right? The one that lacks electrons. So we're going to attack at this position right here. All right, so this will generate our enol intermediate. So first we're going to draw this OH H plus. And this still has a lone pair. Okay. All right. So another water molecule, so this is always going to be surrounded by water. Another water molecule is going to come around and pluck off this hydrogen and make this neutral. Okay, so now we draw another arrow down here. We get so I just flipped the H around. So I just flipped it over. So the H goes here. The COH. Okay. Like so. All right. All right. Did I forget the H here? Let's see here. All right, guys, let's just keep the H in the same place. I just don't want to confuse you guys. So let's put that H there. And sorry about this one. Let's just replace that H. Let's put it up here. Okay. All right. So what this double bond is going to do now is going to protonate the acid form of the H3O that we just generated. So we're going to generate it like that. Okay, so that's actually going to give us our other H here. So now we have two H's on this carbon. But now we have a carbocation here. But we're going to show that this carbocation is stabilized. What can we do to stabilize that positive charge? Like, what can we use? What can we do with these electrons I've just drawn here to help stabilize that? Yeah, you're going to use double bond here, and now we have drawn a resonance form for this molecule here. So what happens here now, this carbon has its octet refilled, and now this positive charge has to be delocalized onto this oxygen so we can further stabilize this charge. Okay, and then here we have two H's attached though. So now this is a resonance hybrid or resonance pair of resonance structures. Okay. Now, actually let me create some space. Sorry about that. Let me just write it right here. Now this water that was generated in the last step, it can now come around, okay, and pluck off this hydrogen. And now we get the final product, which is the ketone, which is this structure right here. So I just follow along what I've drawn, double bonded O. Okay. So if we kind of highlight this end right here, this end is right here. And then the three other carbon atoms, CH2, CH2, CH3, that's this part right here. So that's how the double bond formed. So see how when we form the enol right here, let me just highlight it for you. When we form this group right here, right, it's not very stable, so it's going to rapidly react with acid, and it forms this, and then it can reform this, the carbon, it can reform the double bonded O, the carbonyl, and that is what's going to form the final product. So it rapidly converts to this carbonyl compound because that's more stable than saying having a CC double bond and just a single carbon oxygen bond. So what happens here is we can write like this. So in this step, we're going to replace weaker CC double bond with stronger COO bond. Okay? So that's the driving force between this isomerization. You're substituting a weaker CC double bond into a much stronger, more sturdy C double O bond, and that's more stable for that. Okay? So that's the rationale there for why this occurs. Okay, so for this reaction, make sure you can work through the steps. So practice drawing out this mechanism and convince yourself that this is how this reaction works. Okay, so the key thing in here is that this structure, unstable intermediate. Okay, so it's unstable and it wants to replace some bonds. That's why it goes the way it does. Okay. All right, and then the other products, let's draw them here. You have H3O plus from the acid step, from the last step with water. Okay, and then what this regenerates is basically water is regenerated to continue the reaction, and H plus is also regenerated. So these two species are regenerated to continue the reaction going forward. Okay, are there any questions? Any part of this mechanism that didn't make sense here? Any clarifications? Okay, so there are reaction steps we've seen before. You have a alkene/alkyne attacking H plus, forming a carbocation, and then the nucleophile that remains attacks the carbocation. So it's kind of like we saw in first semester, nucleophile attacking electrophile. Okay. And, of course, acid-base type steps here. Okay. Any other questions on that example? No? All right. So You know, in the homework, you'll see examples of this. Take this knowledge here and apply it to the homework without looking at your notes. And then if you do need to use your notes, please consult them. All right. All right. So that's number 5. We have a few more here. So we're going to go over, let's see. Do I even go over ozonolysis? I guess I do not. All right. Okay. All right. So we're going to go over now the other reaction with water. Okay, so this is with internal alkynes, but we can also do it with terminal alkynes. So now let's go different section here. Let's talk about reaction class 6. Okay, so if that reaction was Markovnikov addition of water, this is now going to be anti-Markovnikov addition of water. So like we saw with alkene, remember hydroboration oxidation? We get anti-addition of OH, HOH across a double bond. We do the same thing for alkynes, but this only applies to terminal alkynes. Okay. So let me just put a note here. In this reaction, we use a different boron reagent. So we use usually R2BH. Okay? Where R equals cyclohexyl. All right? So cyclohexyl, we add cyclohexyl because usually when you add bulky groups to something, usually it's less reactive as a nucleophile. So if we bulk something up, that decreases the reactivity some orders of magnitude. So that's a technique we use. We use steric hindrance to reduce reactivity. Okay? So that's what we use here. Okay. The reason is, remember BH3, borane, we use that for alkenes. Borane is too reactive, so it won't actually stop at the alkene stage. It'll actually go further. So it's too reactive here. So that's why we had to modify the reagent. Okay? So terminal alkyne, prime example is R. Triple bond CH, so a typical terminal alkyne. All right. So usually here, we're going to use something like this. Okay. So, let's use R2BH. So it's usually this reagent, okay? THF. And the reaction is pretty similar to the alkene reaction. So right here, I'm just going to tell you to refer to that reaction for alkenes. So for the mechanism for alkynes here, you don't have to remember that. I usually don't test that one. Okay? Sodium hydroxide. Okay? So what's important here, I'll say here that it goes first through this intermediate. It's a very similar intermediate we saw in the previous reaction, OH, H, But compared to the other reaction there, the OH now is on the less substituted carbon atom. So the carbon atom without the R group. Okay, and then this undergoes again tautomerism. All right, so where the double bond switches with the oxygen. So now those things switch, and we get, in this case, now we have two hydrogens here. An aldehyde. Okay, so that's the aldehyde version of the alkyne reaction there. All right, so here what I'll say about the mechanism. Mechanism is similar to alkene reaction. For this step, okay? So please refer to that mechanism. The reason why I say this, because drawing out the mechanism here for both of these steps will be too long, and it's very similar to the alkene one, okay? So first what happens is you get hydroboration. So you're going to get a boron added to the alkyne. It'll form this alkene group here with a BH2. But then the second step, remember we had that oxidation step where the oxygen from hydrogen peroxide migrates to the boron. And pretty much what happens there is that you get a migration step, and that's the oxidation step of the molecule. Okay, so refer to that mechanism for this step, okay? So I would say refer to that mechanism. Okay, so in other words, you don't have to reproduce it, okay? But you should be able to predict this type of product, and what I'm going to explain now is how tautomerism works in basic conditions. So remember how we did it over here in acidic conditions right here? Remember how we did it in acidic conditions right here? Let's do it now for basic conditions. Okay, so now we're going to draw the mechanism of tautomerism in basic. All right. So tautomerism can work in basic conditions. So what do we have? OH minus. Because look at this. We have OH minus right here. So how does tautomerism work in that situation? So this is going to be able to deprotonate another OH group. So we're going to write the product of that equilibrium here. So this equilibrium will favor that group there. All right. So what happens here are you get two different groups here. Okay. H, O minus. All right. Well, we have to somehow form that double bond. So what can we do with this oxygen? Yeah, resonance. So let's bring that negative charge down to reform the double bond to the carbon and oxygen, like that. And then this is going to jump up onto this carbon. That kind of resonance structure. Okay? So what happens here now is this negative charge is now going to be on this carbon atom. Well, when carbon all has a lone pair and a negative charge, not very stable. So it's actually going to want to, find a willing atom to accept its electrons. Okay, so we have this double bond O already present, this H here, and the newly formed water can actually offer its hydrogen up because it's fairly acidic. Carbon with a negative charge, very good base, so it's actually going to pick up any hydrogen that's relatively acidic. So anything attached to an electronegative atom here. So this we're going to attack this hydrogen, kick off this OH group, and if we draw another arrow going forward, this is going to form our group here. All right, so that's how tautomerism works for the terminal alkyne version here with basic conditions. Okay. All right, so that's for terminal alkynes. Okay. So if you actually added water here, so this is the one that can actually do Anti-Markovnikov. So this is the one that forms the aldehyde. What if you added water to this reagent? Well, if you added just water, mercury, and H+, well, the water will just add to this position, to the more substitute position, as we saw in this scenario, where it added to this carbon and formed it a ketone, okay? So for number 6 here, if you slightly change the conditions, you can actually get the water to attack the other side instead of the least hindered side, okay? So there's two types of products you can actually form in a terminal alkyne here, okay? All right, are there any questions about this mechanism though? So the important part is that what happens here is that this first step right here, so this first step right here, this forms this enol intermediate, okay? All right, which comes from this step. So if we kind of think about, okay, this initially forms this. All right, so remember the boration product. Then the second step is what forms this enol. It gets rid of the boron. Okay, so step number 2 here replaces Br2. Okay, so the Br actually gets replaced by the hydrogen peroxide, and eventually that rearranges or migrates to form the OH. But don't worry about the mechanism, okay? We kind of already went over it last semester there. Okay, then it tautomerizes to the double bonded O. Okay, but are there any questions here? So the only difference here is that you're forming the aldehyde instead of the ketone. And it's based on hydroboration oxidation. Similar mechanism to the alkene one. 4, 5, okay. 36, okay. Any questions about that one? All right. So the best way to practice this, guys, is do the homework, okay? So please get started on the homework. we can expect a couple reactions to appear next week, okay? All right. So let's go over a few more things here, okay? And then I'll write a question on here on the board so we could preview nomenclature a little bit, okay? So, chemistry of alkynyl halides. So we kind of didn't talk about this recently. Okay, so alkynyl halides, another name for this is vinyl halides. So vinyl records, very similar to like vinyl recordings, is actually made from these type of plastics. That's what the where the name comes from. Vinyl recordings there. Okay, so in a vinyl halide, you have an alkene attached to a halogen here. Okay, so the one thing this reaction doesn't do, or these molecules don't do, they do not participate in SN1 or SN2 reactions. And that's because there's no room for backside attack for SN2, and there's no way the carbocation can be stabilized, okay? So no SN1 or SN2 reaction. So SN2, too sterically hindered. The site of attack will be too sterically crowded. And SN1, the carbocation can't form and be stable. So it's very unstable because of the nature of the carbocation is flat. And it can't be stabilized by hyperconjugation, okay? So no SN1 or SN2 reaction. However, you can actually use this to make a Grignard reagent. Okay, so you can add Mg0, and then we can use diethyl ether, okay? So this is just a solvent. We make the reactive intermediate. So the alkene won't actually get in the way of a Grignard reagent. So that's the beauty of the Grignard reagent. And then you can actually use other chemistry here to react it away with. So H3O plus. So let's use epoxide. And here we're going to use our ether solvent there, so diethyl ether. And what happens here is that this Grignard reaction will actually form this product. So remember, this bond is what's being connected. So that's the nucleophilic bond. So this bond right here is the new connection you're going to make. So you're going to make that connection, and remember from the epoxide, attack the least hindered side. So I'm going to attack the CH2 here. The OH comes right out here, and then the rest of the molecule follows. So now you've made a strategic CC bond formation. So that's a powerful tool we have for Grignard reagents. Right there. Okay, so let me explain why SN2 and SN1 doesn't work for these type of molecules. All right, so let's bring this this reaction right here. So here is, whoops. So we have a double bond here. Okay, so here's my Br. So remember in Br, we need to, there's certain orbitals that need to align. Okay, so let me just draw a few here. So remember the orbitals here. All right, so this is just my explanation, okay? All right, so this orbital, in order to do SN2, the nucleophiles orbital has to overlap with this anti-bonding orbital of the C-Br bond, okay? So here's my nucleophile. This would be my interaction I would have to make here. So the thing here is that when this nucleophile tries to approach, there's going to be steric hindrance experienced right here and right here. So it's two sterically crowded. So two sterically crowded, so no SN2 can occur. So no SN2. All right. So two sterically crowded for that nucleophile to approach. Because remember, if it's planar, you can't really rotate those bonds out of the way because of the pi bond. It's keeping it locked. Remember when we built those models, we tried to rotate it. It doesn't rotate around the pi bond, so we can't get that bond out of the way. So two sterically crowded bonds around the pi bond are locked in place. Okay. Now, how about SN1? Okay. So this positive charge. So this CH bond here is planar. So planar CH bond. So unstable cation. Okay, so this carbocation is actually not in the p orbital. Well, it is, but the p orbital is in the plane of the page, so it's not. It can't be stabilized by resin. So unstable cation here. When you have cations on sp2 hybridized or sp hybridized orbitals, they're not likely to be stable. So they're very high to form. Unstable cation, very high in energy. Okay. All right. So that's the last kind of reactions alkenes can really do. Next time we'll talk about the applications of alkenes and alkynes. What are they useful for? And then we'll start talking about delocalized pi electrons. Okay, so we'll do that on Thursday. Okay, so that'll be it for today, guys. Thank you.